So we can see there's a lot of benefit to working with normal distributions because there's a lot of stuff that's going to be able to be done with it. We can tend to find probabilities relatively quickly, and they're fantastic to work with. The problem is not always do you have a normal distribution. So is there a way that we can maybe take whatever we're given, turn it into a normal distribution, and does that actually lead to a lot of the same information? Like, does it ruin anything that we had before? So what we're going to talk about now is how to sample distributions and then give estimators for stuff. So instead of working with values from the original population, we're instead going to focus on values of statistics. So the main idea behind this is there's going to be three kind of big ones that are important for us: sample proportions, sample means, and sample variances. So what happens is if I have a sample of however many individuals, say it's 10,000, but that data doesn't quite fit a normal distribution, what I can do is I can randomly select a fixed number of values, and that's going to give me a sample of the population. Within that sample, I then can find the proportion of individuals that have a characteristic, the mean of that sample, the variance of that sample, so any one of these three. And what I'm going to do is I'm going to keep repeating that process. So if I have a sample of 10,000, maybe I randomly select 50 individuals. I'm going to find the sample proportion for that first sample. Then I'm going to do it again. I'm going to randomly select 50 more individuals. And then I'm going to find the sample proportion for that group. And I'm going to keep doing this process over and over until I have a variety of sample proportions. Now that's going to give me different numbers. And what happens is if I were to graph that distribution, I would see it would actually be something that is normal when I do more and more of these samples. And same thing, if I have 10,000 individuals, maybe I select 50 randomly to start, I find that mean of the first sample. It gives me a number. Then I do it again and I find 50 more individuals. I find the mean of those second group and it gives me a different number or maybe the same. Then I go through and I do it again and I keep repeating this process over and over. And now I'm going to have a whole bunch of numerical values that are means based on those samples. If I were to look at that distribution, it's likely going to be normal. And then I can do the same thing with the variance. Repeat the process, get my smaller sample, calculate the variances. This one will be a little bit different because you're going to see there's going to be a little bit of bias here to it, but they tend to have skewed, so it kind of leans towards one side instead, but that's okay. So we're going to start with an example to see what do we mean by doing this and how does it possibly end up being the same. So we're going to work with a very small data set. You would not do this with 3 data values. It would be silly to find a sample from 3 numbers. But again, this is to prove the point that this is going to work because you cannot do random samples when you have 10,000 things by hand. A computer is going to have to do it for you or it would take forever. So we're going to work with very small numbers to see how does this work out. So we're told a friend has 3 kids with ages 4, 5, and 9. 2 of the kids or 2 ages are randomly selected with replacement from the population. So remember, with replacement is going to guarantee we have independent events, and this way we have that pure random sample. So if I want to look at all of my possible pairings, this gives me my samples of smaller groups. So maybe I pick the first individual, which has age 4. And then again, when I go to pick the second, because it's with replacement, I could also pick the age 4 again. Also, with a person of age 4, I could pair them up with 5 and also with 9. So we've got 4 and 4 together, 4 and 5 together, and 4 and 9 together. Now I'm going to do the same thing. I'm going to pair 5 with each of these and then also with itself. So 5 gets selected first, and then 4, 5 and 5, and then finally 5 and 9. And so you can see for each number, I have 3 possible pairings. So in total, I'm going to have 9 pairings. So with 9, I can first select the 5, or first select the 4, then select the 5, and then I can pair 9 up with itself. So I've got 9 and 4, 9 and 5, and 9 and 9, giving me a total of 9 different samples or pairings. So what I'm going to do to find the sample mean between each of these pairings, I find its mean. And then I'm also going to find the probability at which it occurs. So the probability is honestly going to be the same in this column because each of these samples, since it's being randomly selected, have an equal chance. So any one given sample has a 1 in 9 chance of being drawn. So I'm going to start by listing all of my samples on the side. So we had 4 and 4 together, 4 and 5, 4 and 9, 5 and 4, 5 and 5, 5 and 9, and then finally 9, 4, 9, 5, and 9, 9. So you can see a lot repeats, so you don't have to triple do work for these sample means. So what I'm going to do is I'm going to find the mean of these 2 values. And remember, to find the mean, you add them together and divide by 2. So this gives us 8 divided by 2. The sample mean is 4 for this first one. The mean for the next one would be taking the ages 4 and 5 together and dividing it by 2, which gives me 9 over 2. And that gives me a mean of 4.5. Then finally 4 and 9 over 2 is 13 over 2, which is 6.5. Now I repeat the process with the 5 pairings, but 5 plus 4 is no different than 4 plus 5. So really it ends up being that this is the same. I do not need to do double work. It's 4.5. And what I like to do is I like to now know, oh look, this number has repeated. Next number up is 5 and 5. Well, when you add them together and divide by 2, it just leads back to 5. Okay. Then we've got 5 and 9 over 2, and we haven't paired those up, so that's 14 over 2, which leads to 7. Now moving on to the 9 being selected first, when you do 9 plus 4 over 2, that is exactly the same as 4 plus 9 over 2. So no need to redo this. That mean will be 6.5. And same thing, 9 plus 5 is the same thing as 5 plus 9. So ultimately, this 7 is going to repeat. The only new number now comes from this final one, which is 9 plus 9 over 2, or 18 over 2. And really, when you add the same number and divide by 2, it is the same number, 9. Okay? So these are all of the means of the samples, which is why they're called the sample mean. And if you remember our notation from dealing with samples, we put that bar over top to indicate it wasn't the full population. Now my probabilities, again, there are 9 pairings. Every single pair has an equal chance. So all of these probabilities in this starting chart are exactly the same. So you have a 1 in 9 chance of this particular sample being drawn. Okay? So over here, each sample is equally likely to be picked. Now for my analysis, I actually really don't care about the samples themselves. This is going to be the most important information. So what we also like to do is when we have these repeats, you actually have a higher probability of that mean occurring. So since 4.5 appears twice and each one is that probability of 1/9, you have actually a 2 in 9 chance of this particular sample mean occurring. Likewise, the sample mean of 6.5 occurs 2 out of 9 times, so you have a 2 in 9 chance of this mean occurring. So since the sample means repeat, we can condense this. And this table is actually going to give us a probability distribution. In reality, this one does, but again, it's just not condensed. So I'm gonna write all of my different sample means that I have up here. My lowest value is 4, and that occurs 1 time, so it has a 1 in 9 probability. My next smallest value is 4.5, and that occurs twice. So the sample mean of 4.5 has a 2 in 9 chance occurring. So that comes from these ones highlighted in blue. My next number is going to be 5, and that occurs just a single time. So it is a 1 in 9 chance of occurring. I don't have a 5.5, I don't have a 6, so my next value is 6.5, which appears twice. So 6.5 appeared 2 different times, giving it a 2 in 9 probability of occurring. Okay. And then after that, my next value is 7, and that also appears twice. So that is a 2 in 9 chance of occurring. And then last but not least, my last biggest value is a sample mean of 9, and that occurs a single time from here. So one thing that you might notice now is if you go ahead and add all of these up, 1 plus 2 is 3, 4, 5, 6, 7, 8, 9. The sum of these probabilities is exactly 9 and 9, which is 1. So this is great because now we have a single numerical value for a sample mean, and then we have those associated probabilities. So this gives me a probability distribution, okay? So what I'm gonna do is, we were working with sample means, I'm gonna find the actual mean of the population, and then I'm gonna find the mean of the sample values too, because we know how to do that. So if I look at my population, those are the values 4, 5, and 9. And so my true mean is we add these values together and divide by 3. So 4 plus 5 is 9, plus 9 again is 18, and 18 divided by 3 gives us a mean age of 6. So I want to see, when I created these samples and used these sample means, does this distribution give me the same mean? And if you remember, the way we find that is we sum up each random variable multiplied by its probability. So I look at every value that the sample mean takes on, and I times it by the probability that can occur. So I'm going to zoom out a little so I can see everything all at once. My first value of x is 4, and I want to times that by the probability of 4 occurring. Next value is 4.5, and we want to times that by the probability of getting 4.5. Then 5 times its probability. 6.5 times its probability. 7 times its probability, and finally 9 times its probability. Okay. And just to highlight the ones that have a value of 2 out of 9, that's 4.5, 6.5, and 7 all have those higher probabilities. Everything else is 1 out of 9. So this is really 4 times 1/9. 4.5 times 2/9. 5 times 1/9. 6.5 times 2/9. 7 times 2/9. And 9 times 1/9. So when you're multiplying a number times a fraction, again, you can think of this as 4 over 1. So you then multiply numerators, multiply denominators, but really you're just going to take that numerator and times it by the value out front. So we're not going to use our calculator. This is one we can do by hand. 4 times 1/9 gives us 4/9. And I'll make it look like a nicer fraction now. 4.5 times 2 gives us 9. So we get 9 over 9. 5 times 1 is 5. So that's 5 over 9. 6.5 times 2 is 13 over 9. 7 times 2 is 14. So 14 over 9. And 9 times 1 is 9 over 9. Because these all have the same denominator, I really just go ahead and add all of these numerators. The denominator stays untouched. So if you do 4 plus 9 plus 5 plus 13 plus 4 plus 9, that ends up equaling 54. And then 54 divided by 9 gives us 6, which is exactly what we got when we found the actual mean of the population. So again, this is really to show you that when you take the mean of these samples, it ends up being the actual mean of the population. And that's going to be true when you do this with a lot of data values. So the more samples you take, the better the estimate is. And it ends up being that the probability distribution you create is normal. And that's the major benefit. You get a normal distribution with this chart, which is fantastic. So again, it doesn't look great because it's only 3 values. This is much better for large data. But if your data is not normal, this is a way to look at something that has a normal distribution to be able to then apply what we want, which is awesome. So this is the idea that is called estimators. An estimator is a statistic used to infer the value of a population parameter. So our estimator in the last case was the mean, or was the sample mean from each of those samples. And it estimated the true mean of the population. An unbiased estimator is what we're really concerned with. So an unbiased estimator is a statistic that targets the value of the corresponding population parameter. So an estimator can estimate it, but it might not be a good estimate. It might still estimate, but you can't guarantee it's actually the true value. So we don't want that happening. We want something to be unbiased, which basically means the mean or expected value of your sample distribution is the population parameter. So to kind of go back up here, my sample estimator, my sample statistic I used was I found the mean of this sample. But instead I could find proportions. So I can find the proportion of this sample for one of my different age values. I could find the variance of this sample, which would be a little tedious to go through. And then I would have just a single value to describe that sample. Once you then find the mean of this or the expected value, it should be identical to the true value. So the mean of my sample proportions or the mean of my sample variances would be the exact same as the real proportion or the real variance, okay? So these are the unbiased estimators that we want. Now, lucky for you, that's already done. I can tell you what's an unbiased estimator, and I can tell you what is biased, meaning it won't be exactly right. So we have 3 unbiased estimators, which are the proportions. And the way we denote this is with P and a little hat, we call it above. And what this does is it takes whatever value you're searching for, X, and divides it by that sample size. So this would be the number of successes divided by the sample size. So in that last example, maybe you considered success getting an age of 4. So you would look at in your sample how many 4s there are out of the sample size, which in our case was 2, and that would be your proportion. Another unbiased estimator is exactly what we just calculated. It is the mean, and because it's the mean of a sample, we use X with that bar above it. And then the last unbiased estimator is the one we used before, or we mentioned at the beginning. It is the variance, and we use S squared for that because, again, it's the variance of a sample. So that's where you use that n-1 in the denominator instead. In terms of biased estimators, we have 3. That would be the median of the sample. This is going to end up not being the true population median. Then we've got the range as well. And finally, standard deviation. There is a little caveat with standard deviation. When you're dealing with a large population, the bias is very small. So in that case, we will use the sample standard deviation to estimate. So S is often used to estimate the true standard deviation, sigma. So again, if you're working with a data set of 1 million individuals, when you go ahead and you do a ton of samples from that, you can go ahead and find the standard deviation of that sample to estimate the true standard deviation. That bias is going to be pretty insignificant, okay? So what we've done is we've shown already the mean is an unbiased estimator, because in this example, the actual mean is the same as the mean of the sample. What I'm going to do just for one last example is go through and show you the median is not an unbiased estimator. So again, we're going to work with a small population because it's pretty near impossible to do this by hand otherwise. We're told 3 randomly selected children are surveyed. The ages of the children are 3, 4, and 11. Assume that sample sizes of n equals 2 are randomly selected with replacement from the population. We're going to find the sample median. So the very first thing I want to do is I want to find the true population median. Because with 3 pieces, it's not so hard. 3, 4, and 11 are already in order. Remember, median is the one in the middle, and there is a single number in the middle. So the true median is 4. Now, knowing that there's 3 different actual data values, same as before, we're going to have 3 pairings with each of these, 3 with itself, 3 with 4, and 3 with 11. So there are going to be 9 samples in total. We're going to find the median of each of the 9 samples, and then we're going to summarize the sampling distribution in the format of a table representing the probability distribution. Basically meaning create your big table first with those equal probabilities, and then condense it if there are repeats. So we have 3 different data values, and we have 9 samples to go through. So 3 can get paired with 3. It can also get paired with age 4 and also get paired with age 11. Then 4 can get paired with 3, with itself, and with 11. And then finally 11 can get paired with 3, with 4, and with itself. So if I want to find the sample median, I need the median of these 2 values, which means they have to be in numerical order. Unfortunately, I don't have a number in the middle, so to find the median, I'm going to have to sum these up and divide by 2. So my median in this first case is we add them together and divide by 2. So that gives me 6/2. My middle number is 3, which I could have known because it's the same, so halfway in between those numbers is 3. My next 2 in order are 3 and 4, so my median in this case is the number directly in the middle, which would end up being 7/2. That value dead center is 3.5. Then we've got 3 and 11, that is in the correct order. So the median is we sum them up and divide by 2. 3 plus 11 is 14. 14 divided by 2 gives me 7. Then if we go 4 and 3, putting those in order is the same as back up here. So I really do not need to do any extra work. This median is 3.5. When I have 4 and 4, it's the same number. So the median is 4, the one in the middle. 4 and 11, we haven't done this pairing yet. So we add them together and divide by 2. 4 plus 11 is 15, divided by 2 gives me 7.5. 3 and 11 we have already done, that is back up here, so this median is going to be 7. 11 and 4 we have done not too long ago, so this median is 7.5. And then finally 11 and 11, it's the same number, so the median is 11. So my probability, 9 samples, again, same equal chance for all of them. So you have a 1 in 9 probability. Now to condense this, I want to see what repeats. So we've got 3.5 appearing twice. We've got 7 appearing twice. And then we've got 7.5 appearing twice. So our repeats are those values. 3.5, 7, and 7.5. And they each appear 2 times. So the probability of getting this as your median is going to be 2 out of 9. So condensing down to my probability distribution, going back up here, my smallest median is 3. Then it's 3.5. Then it's 4. That's my next one. And then after that, it's 7, 7.5, and finally 11. Only these 3 repeats have a probability of 2 out of 9. Everything else has a probability of 1 out of 9. And so if I add this up, 1, 2, 3, 4, 5, 6, 7, 8, 9, giving me 100% probability. So this is a probability distribution. So now what I want to do is I want to figure out what is the expected median from here. So I'm really finding my mean of this sampling distribution. So my mean is, again, taking the sum of each of these possible outcomes multiplied by its probability. My first possible median is 3, and we want to times that by the probability of getting a 3. Next one is 3.5 times the probability of getting a 3.5. 4 times its probability. 7 times its probability. 7.5 times its probability. And then finally 11 times its probability. So filling in those probabilities, the probability of 3 is 1/9. Probability of 3.5 is 2/9. Probability of 4 is 1/9. Probability of 7 is 2/9. Probability of 7.5 is also 2/9. And finally, the probability of 11 is 1/9. So if I go to multiply these, again, really you just multiply in that numerator, because this is really like 3/1, and you multiply fractions across. So 3 times 1/9 is 3/9. 3.5 times 2 is going to be 7/9. 4 times 1 is 4/9. 7 times 2 is 14/9. 7.5 times 2 is 15/9, and 11 times 1 is 11/9. So everything is out of 9. So if I do 3 plus 7 plus 4 plus 14 plus 15 plus 11, that's going to end up being 54, which leads me to 6. So my estimator for my median is 6. But unfortunately, that is not the true median way back up here, which is 4. So when we ask, is the sample median an unbiased estimator of the population median, the answer here is going to be no. The sample median is not actually equal to the population median. So it doesn't target the population median. So because of this, this is not a good estimator of the population median. So that is really it for this section. You can see these problems definitely take quite a bit of time, so you can't reasonably be given a ton of them on any given test, especially if median, not so difficult to calculate for 9 things. The mean also, back up here, not difficult to calculate for 9 samples. But if you had to find the variance, that would take you a very long time, which is why I didn't do it in this video, because otherwise it would probably be like an hour and a half long. But the idea is you'd have to find the variance for the sample, which would require you finding the mean, subtracting the mean from each of those values, squaring them, and then going through and finishing that process. So it could be quite time consuming. But again, The three main pieces that do lead to good estimators and are unbiased are sample proportions, sample means, and sample variances. Those are going to be the best that lead to nice results.